Okay, I didn't know it did that before. All right, so there's two documents here. One is the absorption spectroscopy document, and the second one is an Excel sheet. Okay, so you'll have to open up both of those. Essentially, what you're going to be looking at is this. So let's. Share this here. All right, so this is the Word document. Okay, so this is essentially a lab report. Okay, so as I said, my focus here is going to be on conclusion writing, since that seemed to be where we were struggling with in some of the labs that I was grading. So most people did fairly well on conducting the actual experiments, collecting the data, and so it was really the conclusion parts that we need to work on. All right, so what you have here is an absorption spectroscopy. So you don't really need to know too much about this. Essentially, absorption spectroscopy is, if we look down here at this picture here, it is a method by which we can use to calculate things like concentration. Okay, so we have worked within the past chapter or so, things like molarity. So how do we be able to calculate those kinds of things in unknowns? Is absorption spectroscopy deals with passing light through a sample, and then we're able to essentially equate the amount of energy absorbed by the sample to its concentration. Okay, and so this lab here works pretty much like the physical properties lab that we did conduct. Okay, so in this case, standards were put together. You have I think there's 3 standards, plus there's a blank, and the main stock solution is also part of the standards. And so you have dilution. Okay, so we've done some dilution stuff. So you have dilution equations that calculate the concentration of the various standards. So there's 4 standards, there's a blank, or 5 standards, there's a blank, 3 dilutions, and the stock solution being the highest concentration. And so we're able to measure the amount of light going in and the amount of light going out, and then the relationship of how much is absorbed by the sample as a function of its concentration. So in this experiment, I've kind of outlined kind of the general procedure that would have been taken. A calibration curve would be generated. So here you see the blank, the various molarities, and the stock solution. And so just like our first experiment, we would expect that our unknown would be somewhere between these values. We have our equation for the line, y equals mx plus b, plus an r squared value, which again tells us how linear our data set is. You would plug in your unknown value. So you would do an unknown into the instrument as well. It would record its absorbance. And so you plug that value in for y and solve for x. Okay. And so essentially just like we did for the physical properties lab. Okay. So the data is all captured within the Excel sheet. And so what you'll then notice here is missing is the conclusion. Okay. So you guys will have to write the conclusion. Right, so you will give me back essentially this document. So it's a Word document. It'll already be filled in, and then you can fill in the conclusion part and submit it as your report. Okay, so let's look at the Excel sheet. Okay, so we can look at what this looks like, and then we'll talk about the conclusion part. right? So let's zoom in here. All right. So in this experiment, we have a stock solution that is 0.42 molar, right? A total volume of each sample was 25 milliliters. And so essentially to make certain concentrations, 3 milliliters of the stock was taken, 7 milliliters of the stock was taken, and 12 milliliters of the stock was taken. Each one of these was diluted to 25 milliliters. And so this is an M1V1 equals M2V2 equation, okay? And so here you will see all the equations are already done. So here you'll see the actual M1V1 equals M2V2 equation. So here we have the molarity of the stock solution, molarity, M, times the volume that we used of it, only 3 milliliters, divided by the total volume, 25 milliliters. And so this gives us the concentration of essentially sample A, okay, which is about 0.015. So you'll see that most of them are about roughly the same value. Solution B, again, is a dilution, except here we increase the amount of stock that we were using from 3 milliliters to 7 milliliters, which will increase our concentration. Again, you have an M1V1 equals M2V2. We'll multiply and divide. Each sample is 25 milliliters. And so now our concentration, our second stock solution, or our second standard is 0.1 molar. Concentration is 0.2 molar, and the stock solution was 0.42, okay, which is again what we were given, right? So section A is just the raw data, okay? So this is just strictly raw data. Nothing's been calculated. The unknown values here are in the same order as they are at the bottom, okay? Everybody took the absorbance of their unknown. Again, this is not a calculated value, so this is why it's in the raw data section. Section B is the calibration curve set of data. So obviously water is our blank, so it's a 0 concentration. And then the stock solutions or our standards go up in concentration until they reach the stock solution, okay? The absorbance of each solution was taken. So in each row, okay, so this is in one row, that's a student's data, okay? So what you see as an example is highlighted in blue is one student's data, okay? Is this particular student took unknown number 1, they use this volume, these volumes of the standards, they had these absorbances that went with those standards, okay? So each row is a different student's data, okay? And then it was all compiled into this spreadsheet, right? Now, when you have a big data set, okay, when we did this in the physical properties lab, you each did your own graph. But in this case, we don't have when you have a big data set, you generally don't do graphs for every single person. So we just have Excel do the calculations for us, okay? So we need the slope, right? So if we're doing the graph, okay, which I put in here, if we're doing the graph, we need to calculate the slope, okay? But I need the slope of everybody's data, not just the slope of the one person's data. So here you see the 4.98 is the slope, and that's essentially the graph that's over here. So the stuff in blue is just the one person's set of data that I highlighted as an example, okay? But I need the slope for everybody's data. And so you'll see the equation here, okay? I have my slope is an equation that can be calculated. So I have my y-axis, and so I have my y-axis, my absorbance, and I'm gonna have my x-axis, my concentration, right? And so Excel can just calculate the slope value rather than doing the whole graph. Same thing with the intercept. I left all the equations in there. Again, you're not strictly doing anything as far as the equations in here, so it's fine for you to have these. Presumably, if you learn something from this, is that you can do these calculations without doing a graph. Okay, the r squared value. So you see the equation for that is RSQ. So the r squared value is just like it is on the chart. if we've forgotten what the R squared value is, this is a function of how linear the data set is. Okay. So the closer to 1 means our data is more linear. So you probably would have done this with our first lab as you were plotting your data. And as I said, values that are as close to 1 as possible are better or more linear data sets. If we don't have any particular way of doing things like error analysis, it's a good way to check that our data is at least somewhat precise. Okay. Here's the absorbance of the unknown, which is the same as it is up here. Okay, so I just took this. This is the same order as everything is. It's just copied down here to fill in my Y value. And so solving for X, I can't change it now, but essentially solving for X is a function of putting in Y, subtracting the B value, and dividing by the slope, right? And so unknown number, so this particular student had unknown number 1, okay? And we see the concentration for that student's data. All right, now what you have to do is the only data analysis you may have to do is to give me a number for unknown 1, okay? All of these students had unknown number 1, okay? So essentially these are replicates, okay? So you have a trial here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, roughly 11 replicates, okay? Which is a good way to do your data, is you collect a lot of data, and in that way you have some statistical confidence in your results, okay? So the only thing that you may have to do is to tell me what is 1 and 2, okay? So that is your goal, right? So when you look at the purpose of the experiment, let's go back to the Word document here. To identify the concentrations of the 2 cobalt solutions. Okay, so just like in the physical properties lab, I want to know what is the concentration of unknown number 1 and what is the concentration of unknown number 2. Okay. All right, so again, now back to the conclusion writing again. So when you're doing your conclusion, things to think about when you're doing this writing, okay? Remember that the conclusion is not done the same way for every professor. So it is somewhat of a, more kind of variable thing that people can have a preference of what you should put in there. But nonetheless, how conclusions are written, they are generally focused on providing someone with all the information. Because when you have to look through that whole data set, that whole spreadsheet of data, you can't leave that up to someone else to interpret, okay? We can't leave things up to a client to interpret. So again, if you go to the doctor and they do a blood panel on you, and they don't just give you the blood panel with the data, right? They don't leave it to you to figure out what do all those numbers mean, okay? So even though you may see like the error bars on things like the cholesterol, where they tell you that normal is between these 2 numbers and you're on the high end, sometimes those numbers don't necessarily are not indicative of a particular health issue by themselves. So when you take other, blood things and put them together, that there may be some combination of those facts that provides an overall information about your general health, okay? While like your some like blood, nitrate level, along with other things like sugar or your cholesterol and triglycerides and other things may indicate that you have, some sort of diabetic condition, or you have, some sort of, renal failure or something like that. That, just because one number is high or low does not necessarily give you any information by itself. And so you shouldn't be relying on giving your client or whoever a big data set and expecting them to pick out the information. Okay. So you need to give them data. Okay. You need to put data in the conclusion. What do they want to know? Okay. Again, when I explained this in the very beginning, I'm paying you for this information. I want to know what's in my water. Okay. What is the concentration of these things in these samples? Okay. I need to know that. Okay. That's what I'm paying for. So we have to avoid things like just simply reiterating the procedure. Okay. You already have a procedure section, so you don't need to reiterate exactly what you did. If there are particular steps that are important, those things can be highlighted. Okay. But you want to focus on, if you're going to talk about the procedure, we need to think about what part of the procedure was really key for determining what the unknown was. Okay. We have to watch data that we put in there. Okay. So like for the physical for the separations lab, okay, for example, right? Telling me that you have 0.5 grams of iron in your sample doesn't really mean anything. Okay. Unless you provide the context of things like, what was the total sample mass? Okay. So if I know that the total sample mass was 1 gram and then 0.5 of that was iron, that gives me some context for that number. But again, you're also expecting that your client is doing math that you should already have done for them. Okay. So we have to think about those kinds of things. Your client is not paying you so that they can do math. Okay. They're not paying you so that they can search around through spreadsheet numbers for the information that they're after. Okay. They shouldn't have to do the interpretation of the data set. Okay. You have to lead them to the answer. Okay. But you have to give it to them in some sort of logical order. You can, give it up front. Here, sample 1 is this concentration, or sample 2 is this metal. Okay. You can give that information up front and then further explain how you got that information. Again, remembering that one sentence is not a conclusion. Okay. It's just like, again, back to the blood panel thing. If I just tell you your cholesterol is 120, it's one sentence. Your cholesterol is 120. What does that mean? Okay. You have to give some other information. You have to lead them towards understanding what do these numbers mean. Okay. How is it conducted? What are the kinds of experiment parameters that we have to consider? Okay. How many samples in general were taken? And again, is this a single sample? Is it like in this particular one, there was 11 samples? Are they in duplicate? Some information that allows you to convey that there's some amount of effort that went into doing the analysis, other than having to read your procedure. Okay, so again, I gave this kind of guidelines in the very beginning. Okay, what was the purpose of doing the experiment? Reiterating to, again, your audience, what is the objective? Okay, what are we trying to get at? Right? How did we go about doing it? Okay, now sometimes, again, this is not reiterating the procedure. Sometimes there's a step in there that's important, but sometimes there's a method that we used in order to determine the unknown. Okay, or to determine some analysis that was used. Okay. Sometimes that's important for people. Sometimes there's important information about how you went about conducting the analysis. Okay, we see this often in things like when people are doing vaccine research. Okay, did they collect all of their data by dumpster diving into VAERS? Okay, the vaccine effects database. Okay, are they just simply looking at numerical data out of a database where they didn't do the actual data collection, where they have no primary source data? So if you don't have context for things, then again, the method in which you did your analysis can affect or give people context for the conclusions that you're drawing. Okay, what was the result? Okay, again, this should include numerical values, especially if we are doing analytical chemistry where we are putting things into instruments and getting numerical values. If you had a graph where you're collecting numerical data, then there's a number. Okay, again, if this is a single unknown that we ran a bunch of times, there's probably a single number that goes with that. It shouldn't be things like it was between 0 and 0.42. Well, obviously it's between those two numbers. That's what your calibration curve was. Okay, but it shouldn't be everything between, if you go to the doctor for symptoms that you don't want to know, well, it could be the flu, could be coronavirus, could be a common cold, could be indigestion. Okay, any one of those things, it's kind of a wide range of symptoms or of outcomes of those different things. It's like, especially with it could be coronavirus, could be Ebola, one of the two. It's like, okay, well, that drastically affects the information and outcome and treatment and things like that you're going to be recommending. Okay, so you want to be specific when we can. Now we are doing numerical analysis or analytical analysis, so we can be specific. There should be a single number given that we try and drive towards to give our client a single number rather than a range of values. Okay, especially if the range of values has some context. Okay, when you get your cholesterol, they may have done 7 or 8 samples or 7 or 8 runs, but they give you a single numerical value for your cholesterol. They say your cholesterol is 120, and they say this is the normal range of where it should be. Okay, but they don't tell you your cholesterol is between 100 and 120, and the normal range is somewhere in there as well. So it's confusing when you give ranges, especially when you have a numerical value. Okay, so you can give a single numerical value. Now, the last part was analysis, like does the number mean something further? So again, in these cases, for a lot of these experiments, the number doesn't have any other significance. Okay, it is just the concentration of an unknown. So we don't need to put it in context of the concentration for the cobalt solution means that you have some sort of health condition, or that you can't drink this water because it's bad for you or something like that. We don't have any information about the conditions of the sample that we have some further analysis to do. Okay, we often do this in like the 112 class. We do hard water analysis where we're looking at magnesium and calcium buildup in our water. So it's a common thing that we have at home of you have hard water at home. It creates like a lime buildup sometimes in your tub and stuff like that. So, but just because something's hard, the question becomes, well, does that mean it's safe? Like, should I not drink that? Do I need to have a Brita filter? Do I need to do something? Do I need to, have some sort of treatment done to my water? There's some further analysis or recommendations that can be made based on the available information. Okay, but for some of these labs, there isn't that other step. Okay, but we should be focusing on giving a numerical answer. Okay, so you'll do the conclusion. I think I put on the website. Let me check. Check our calendar. So let's say So next month here. Okay, so I guess, oh, okay, makeup lab assignment, there it is. All right, so it says 17th. Okay, so this lab is due on the 17th. Okay, I will have another one as well. Again, these are online. We're entirely virtual here. The dates are entirely arbitrary. Again, it's when you finish it, you can turn it in, just marking a date of when things are due. Again, the bibliography is due at the same time. So again, prioritize your work. Get on, again, I can move the makeup assignment, lab assignment due the week before, so that you basically have every Friday, you have something that's due. Actually, why don't we just go ahead and do that? All right, so, but again, that gives you 2 weeks to do this particular assignment. All right, so that's still plenty of time. So this week, don't forget, we have journal assignment that's due. The second journal assignment is due. Then this makeup lab, your bibliography. Okay, so I will put extra guidance into the journal article review for you to add your topics to it. So I mentioned that last time about adding our topics in there into the journal article. So you should have some semblance of an idea of what you want to do for your journal article. Okay. Again, lots of current events that are big science that are very pertinent to our current status, that are easy topics to pick as far as doing work or doing a research paper on. Again, I have already spent time trying to explain to people why it's not like the flu, and how we can't be blasé about these things, like just because it's not, we haven't, because 30,000 people haven't died yet from it. So again, it's there's plenty of science to do a research paper on our current event issues, should you so choose. Okay, so again, journal article due this Friday. The makeup lab will be due on the 10th. Bibliography is on the 17th. So let's talk about the bibliography. Let me see if I can, while we're talking about stuff, before we get into the back to the chapter. All right, so let's look back at our research paper here. All right. So, all right, since we haven't talked about the research paper in a little while, okay, the library retrieval, 50 points, okay. Not that makes very much difference obviously for our pass-fail situation, but nonetheless, again, these are educational skills that we should be building over time. And this is a great assignment, especially if this is one of your first times writing research papers. A lot of other higher level courses in other universities are often moving towards research paper driven courses. So especially if you are doing, it really doesn't matter what the subject is, whether it's anything from social or hard sciences. There are often times when a physical exam is not how classes are given at the upper levels or in graduate classes, particularly where there's more focus on having you write a research paper. And when my wife was doing her stuff, she was writing 20-page papers for every class, and that was like the midterm. And then she did another one, another research paper for the final. And so where you don't have exams, and your ability to conduct research and synthesize information and convey that is an important way to demonstrate what you've learned. Okay. And so this is a good way to to ease into that, because again, it's only 3 or 4 pages. It's not overly long, especially even at the undergraduate level. Okay. So the 18 sources, again, I'm not being as strict. I mean, again, these are the categories that I would like you to think about, because we should be comfortable with drawing information from various sources. So we should be able to find information from various sources. Okay. Especially now if you're working virtually, emailing the librarian to get help, or chatting with them on text and things like that, or on the chat functions from the library are good ways to get help. Okay. So again, the grading here, I'm looking for the 18 sources to start with. Okay. After you do the 18 sources, if you have 16 sources, I start your percentage at 16 out of 18 before I even start looking at the rest of the formatting. Okay. Things that I'm looking for are that you're following the proper format. Okay. Things like journals. Okay. A journal in this citation format are italicized. Is there things like the indent and the italics being done properly? Okay. There's the proper author name, date associations, and do you give the citation links when necessary? Okay. One thing in here that I caution against, if you again are not familiar with this, when you're taking stuff from the library, from the Nova library, it often will give you a link. Okay, but that link doesn't work. Okay, that link doesn't work because it's referencing a paywall source. Okay, so if you're using the link from the Nova library and you were to give that to a friend, they can't click that link and get in there. Okay, because only you are getting in there because you have the access to the site. Okay, so be cautious with those links given from the Nova library. Okay. So things to help you when you're doing your citations, things like the Purdue Style Guide, the citation machine. And so if we look at, and so what you should be giving me will look something like this. Okay. I don't need any kind of bibliographic citation. I don't need, there is no requirement or thing that says you need to write like a paragraph or something about the site. I don't need any of that. Okay. All I want is like this page right here. The citation, 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 citation. Just give me the citations. Okay. For the sources that you want to do. Okay. Keeping in mind, again, this is a specific format. Okay. APA has a specific format. The indent is specified, is called out in the citation guide. Okay. This is a half-inch citation after the first line. Okay. Figure out how to do that. Okay. It is not where the first line is indented and the rest is not. Okay. Paying attention to format is important. Okay. This is a specific format that that I'm looking for. And trust me, other professors, they are anal retentive about these formats. Okay. And if you get any part of this wrong, there are generally often points off in other courses. Okay. People take this extremely seriously, and APA is an easy source. Okay. This isn't like trying to do Chicago or something else like that is far more tedious to try and pick up. Okay. But things like, the last name and first initial. Okay. These are not really strict or difficult things to put together. Everything is The journal is italicized, things like that. Okay, so this is what I'm looking for. I'm looking for 18 of these. Okay, now in a general reference section for APA, they are alphabetical. You can give it to me that way. Okay, you can give me your 18 sources alphabetically. That's fine. You can also group them into sections and say, here are my journal articles. Here are my books. Here are my magazines. Here are my newspaper articles. Okay, that's fine if you want to put them into categories for me. Okay, it's perfectly fine. I don't care about that. I am looking that you gave me 18, that you did the citations properly. Okay, those are the two things that I'm focusing on here. Okay. All right. Let's see. Back to the website here. Okay. All right. All right. So yeah. So this first submission, again, your submission link. Okay. 18 sources, APA format. The guidelines are here. Again, don't worry too much if you don't have exactly in these categories these amounts. It's fine. Okay. I'm just giving these as a guideline of where you should be focusing on. All right. But that being said, again, if you don't give me 4 of everything or you're missing some, that's where the problem is. Okay. I want 18 sources. Your topic may be where there aren't, many reference books on that you're going to include, because maybe more of your articles are in scientific research articles, or maybe they're more in newspaper articles or whatever. Okay, so there is some leeway here in where you put your categories. Okay, as long as there are 18 total. Okay, that's what I'm shooting for. All right. Let's see. All right. Yes, all 18 sources are APA format. Okay, and again, another thing to keep in mind too is a lot of that stuff, if you get it from the NOVA library will give you the citations. Okay, you can get the citations straight from the NOVA library. Okay, so okay, so like I said, this is one of those tricks in here. So if you're if we're looking at sources, again, whether these are academic articles or maybe we want, newspaper, even the newspaper articles. When you go into the art, when you go into the citation, it's over here, right here. Okay, everybody see the little cite button right there underneath the save? Okay, when you click on the cite button, there are, here's the Brazilian National Standard Citation. Okay, the AMA, APA, Chicago, Harvard, another Chicago, MLA, Vancouver. Okay, so there's a whole bunch of different citations in here, and yours is right here. The only difference is that when you copy and paste this, you get some formatting issues. That when you copy and paste this into Word, okay, this is what you're going to see. Okay, so if we take this, and we go back over here to Word. Okay, I me go over here to Word and I go to, right? You get some weird kind of gray, background thing. Okay, so that's weird. Or if you try and do, some other kind of, unformatted text. Okay, then it takes out the italics. Okay, there's no indent, there's no italics. So going with this is not going to be the proper format. Okay, so you can't just, it gets you most of the way there. Okay, so, but it's not going to give you exactly what you need. Okay, so you're still going to have to do some legwork to get the right format right in the right spot. Okay. One other thing that's important here. Okay, especially for some. Now, I'm not the most detail-oriented person. Okay, so it doesn't always, catch my eye. But if you have but if I'm looking through here and you've got, Times New Roman, and then all of a sudden this is clearly some other kind of format, again, I'm not looking for this. I'm not saying this is, like I'd take off points for this. I'm just saying that we should be trying to develop our professional skills, okay? As a professional student, you should be working to push your skills beyond just simply just vomiting this onto a page. Okay, we should be working on our soft skills of making sure that all of these things are the same format. And trust me, it makes a difference. And I see this in my regular job. I see the GS whatever 15s putting together PowerPoints, and there's like 7 different font types because they copy and pasted from different places into a PowerPoint, and it looks like I gave my the PowerPoint to my kid, and he's over there with a crayon scribbling on it. Okay, it looks like trash. Okay, so take an extra second, highlight everything on the page and put it all in the same format. Okay, or the same font type. Right, just it helps, okay, to work on these little skills along the way, okay? All right, let's see. Any other questions on the bibliography here before we move away from this? Other questions? All right, so why don't we take a 5-minute here so we can change gears, and let me set up the PowerPoint, and we'll get over to that. Okay, so you have the replacement lab. All right, okay, so our meeting is being recorded. All right, so let's look at where we left off. All right, so we left off with talking about precipitation reactions. All right, so I did get some extra guidance on doing things like practice problems. So what I'm probably going to do is I will have another video at some point of my jerry-rigged practice problems that I will set up. So I'm going to try and set up and work through some practice problems, and I'll just record it and then post an extra video of practice problems being done. So it may not be a whole lot of practice problems, but at least you'll get to see some being worked out, and so we can focus on some practice problems that are things that you should be able to do. Okay, especially for things like the chemical reaction ones, the stoichiometry. They're not easy, and so I sympathize with anybody who's if we're trying to figure out how to solve these kinds of problems, especially if we don't see them being done. It can be difficult for a couple of times. Again, the methodology is the same for solving most of them, but it's going through and seeing how they're worded, seeing how they're written, what kinds of information do I need to do, how can I organize them, and then how do I solve them. Okay, so I will put something together. I'll probably start working on that tomorrow. Same thing with these kind of precipitation reactions. Okay, so we talked about that the bulk of these are, or all of these are going to be what are called double replacement reactions. Not all of them, but the ones where you have to come up with the products are double replacement, which, as I talked about last time, are when we are going to swap partners for the cations. So the cations are going to swap partners. And so instead of the potassium with the iodide, you're going to get the potassium with the nitrate and the lead with the iodide. Okay, and so that's what we see over here as products. All right. The other thing to keep in mind here, as I mentioned last time, that's key to coming up with these answers, are that the things like the lead don't change their oxidation state. So if we know this is lead 2+ right here, which you should, if it's lead 2+ here, it should be lead 2+ over here. So that allows you to put that molecule together, because you still have to balance this. Okay. So double replacement is just swapping the ions. Okay, so they're like just swap where the positive ions are, and that creates new molecules. Okay. All right, so our first step was doing what we call the molecular equation. So this is where we have a full balanced equation, right? We have to swap the partners, we have to balance the equation, and then we have to assign what happens to the ions after they've remixed. Okay, what happens when they come into contact, and these come from things like our solubility rules. Okay, so the solubility rules, you're going to have to, well, okay, let me rephrase what I would normally say. Normally, I would say you'd have to memorize these, but presumably you probably won't need to, since it's got to be online. So in any case, the solubility rules are important for determining the answers for these problems. Okay, so we had a couple different problems that you can see. Number one being like this example 9 here. What happens when we just put them in solution? Will they dissolve or will they not dissolve? Okay, or things like, if I give you 5 salts, how many are going to be soluble, or how many won't be soluble, or or variations like that. Okay. The precipitation reactions, there are a variety of equations that come with this. The first one being, if I give you the reactants, you might have to give me the full molecular equation. Okay, so this first step was called the molecular equation. All right, so we did this last time. All right, so we left off last time with the second type of equation, which is the total ionic equation. All right, the total ionic equation is one where once we have the molecular equation, we separate everything that's aqueous, okay, into their ions. So here we separate the silver nitrate into the silver and the nitrate, the sodium chloride into the sodium and chloride. The only thing we don't separate are solids, liquids, and gases. So the silver chloride here is simply silver chloride again, and then the sodium nitrate is separated into its ions. Okay, and so this would represent the total ionic equation. This is one of the possible answers, is, or questions. What is the total ionic equation for this reaction? Okay. Now, one of the things that we get from this, though, okay, if we look at this top one here, we have potassium hydroxide and magnesium nitrate, making potassium nitrate and magnesium hydroxide. Okay, so if we separate everything that's aqueous, okay, we get the total ionic equation. All right. Now, new kind of question that comes with this is what we call spectator ions. Okay, so the question may be, what are the spectator ions in this reaction? The spectator ions are like spectators in a sport. they aren't doing anything. Okay, they are sitting on the sidelines, not participating. And so in this reaction, okay, we have to think about what things are interacting with each other. Okay, the spectator ions are the ions that have not changed in the reaction. So here we have potassium iodine, or the potassium ion is still a potassium ion as a product. The nitrate ion is still a nitrate ion as a product. So they haven't done anything. They've not physically changed. They haven't interacted with anything. And by interactions, again, these are precipitation reactions. So the reactions are precipitation. We're looking for the formation of solids predominantly. Okay, that's not always the case, but for the most part, we're looking for solid formation. Okay, so if they don't do anything, they're not reacting. They are spectators in this reaction. They are just simply there, floating around in solution. So identifying them is one of the questions that you may have to do. Now, here's the key. Those rule number 1 ions, let's go back to those. Those rule number 1 ions, okay, these ions are always soluble. So that means if we are looking for things that are forming solids, they are not going to be these, which means that in reactions where we are looking at looking for spectators, again, knowing the rule number 1 ions potentially could identify spectator ions. These are always going to be spectator ions in these reactions because they're not going to be forming solids. Okay, so they are generally going to be on the side spectating. Okay, and so here you see the potassium, group 1, and the nitrate. Again, both of these are rule number 1 ions. So knowing that they're rule number 1 ions automatically puts them into our spectator ion category. Okay. Now, once you take the spectator ions out, okay, you have our last equation. Okay. Here we have our total ionic again. This is our silver nitrate, sodium chloride, making silver chloride and sodium nitrate. Right? If we remove out the spectator ions, the nitrate and the sodium, what are we left with? Okay, we're left with the net ionic equation. So like your net income, okay, after they've taken out the taxes, you have your net income. We have our net ionic equation here is what's left over after we've removed out the spectator ions. Okay, so you're left with the silver and the chloride making silver chloride solid. This reaction here again would be balanced as you do this. Okay, this is the net ionic equation, which is the third reaction we should be able to come up with, given any of these. All right. So example 11 here is a excellent overall example. Okay. Sodium hydroxide plus lead nitrate gives us what? We want to know what is the molecular equation, what is the total ionic equation, what is the net ionic equation, and what are the spectator ions. Okay, those are 4 different. Now again, you saw how the questions were. This is probably more of a super question. So again, each one of these may be individual questions on the test. Okay, like what is the molecular equation? What is the total ionic equation? What are the spectator ions? What is the net ionic equation? So we're not likely to see all 4 of these jammed into one. Okay. All right. So our first step here is identifying just what are we mixing? What are we getting out of this? And so the positive ions are going to swap partners. So the sodium is going to swap with the lead. And so you're going to end up with the sodium nitrate and the lead hydroxide. Okay. The lead is 2+ over here. So it is still 2+ as a product. Okay. So that means we get the lead 2 hydroxide because we had lead 2 nitrate. Okay. And then we have to determine what are the states of those. Now, sodium and nitrate were both rule number 1 ions, so they're both going to be aqueous no matter what. So their result is aqueous. Hydroxides from our solubility rules were generally insoluble. Okay, so the result of then is then the lead hydroxide is going to be insoluble as a solid. Okay, and then we want to balance this. And so we get a balanced molecular equation. Okay, that's our first step. Okay, the total ionic equation. Okay, anything that is solid, liquid, or gas is not separated. We separate the aqueous things. So the sodium and the hydroxide are separated. The lead and the nitrate are separated. The lead hydroxide is not separated as a solid, and the sodium and nitrate are separated. This is the total ionic equation. We separate everything that is aqueous. Okay. Spectators are anything that hasn't changed from the reaction. So in this case, the nitrate is still a nitrate, and the sodium is still a sodium. So nothing has changed in those two particular ions, so they are spectator ions. They are also our rule number 1 ions. So again, if you can just identify those rule number 1 ions, they help you to eliminate out particular answers. Okay, we eliminate out the spectator ions, and what is left over is our net ionic equation, which we would have to balance and make sure is balanced. Okay, so you have lead and hydroxide making the lead hydroxide. Okay. All right. Last thing here that we're going to talk about here, we'll just talk about the acids and bases. So our goal here is to identify acid-base reactions and calculate molarity changes. All right. Now, some of these fall within the stoichiometry section. Okay, so if we're doing things like calculating, if I have 12 molar HCl and I want to know how much sodium hydroxide do I need, that's essentially a stoichiometry problem. So some of these problems, as far as calculating molarity changes or calculating volumes of neutralization reactions, fall within our stoichiometry stuff. Okay. All right. So first thing first. Okay. This is an important slide. Okay. This slide here will save you time in 112 if you're planning on taking 112. Okay. It's important now and it's important later. What are the strong acids? Okay. So by definition, we talked about what was a strong acid previously as a definition, is that it separates 100% into its ions. So these compounds, these acids, separate 100% into their ions. So you have hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, perchloric acid, chloric acid, and sulfuric acid. Sometimes you'll see lists that don't have the chloric acid on it. It's, I include it in this list, but there's oftentimes lists that don't have chloric acid in there, but in this case, it is included here. Okay, so the questions that come from this are identifying which ones are strong acids. Well, guess what? These are the only ones. These are the only strong acids. These 7 of all the acids are the only strong acids. So if you just memorize and know which ones are strong acids, should you ever be faced with a question of identify the strong acid, it must be one of these 7. Okay. Again, there are lots and lots of acids, but there's only 7 strong acids. Okay. So knowing these can save you time. This is also used in 112 because there's a whole chapter on acid-base equilibrium, which again hinges on weeding these things out and focusing on weak acids. Okay. So The weak acids only partially separate. Okay, so as things like what's not on this list for things like here you have HCl, HBr, and HI, so clearly you have halogens, but HF is above here. So HF, as it donates its proton, it also, the fluoride is so electronegative, it sucks it back. And so you have a little bit of HF that's present. So you have HF, you have H, and you have F. So there's always a little bit of the actual molecule in the solution, so it doesn't separate 100%. Okay. All right. For us, our strong bases are going to contain hydroxides. Okay. Generally, our strong bases are things like the alkali metal hydroxides. You don't really need to know specifically which ones. I mean, usually things like potassium hydroxide, sodium hydroxide, magnesium hydroxide, those are, that kind of group in the periodic table that are all kind of close to get together one another near the top. Those are generally your strong bases. Generally, your weak bases are going to be things like ammonia or other type of nitrogen-based bases. Okay. So we're not going to talk about, or we're not going to calculate pH. Okay. So I'm just giving you this information so we can have a frame of reference about what acids are. Okay. Acidic scales range from 1 to 14. Okay. So this is the acidic scale. So things that are highly acidic are lower in number, and things that are alkaline or basic are higher in numbers. And this becomes, then the reason for this is because the calculation is a negative log calculation. So if you're familiar or not with log calculations, the negative log meaning that if it has more of the proton, okay, that's what we're looking for, is like HCl has protons, right? So if it has a lot of protons, then the negative log is going to make that number be smaller and smaller as it goes down. Okay, so as the protons go up, the pH goes down, right? And so the smaller the number, meaning the more acidic it is. Okay. Again, the neutral. So you have 3 regions here. You have acid, base, and neutral, right? So generally, our body generally works right around the 7 area-ish. Okay. Milk and things like that tend to be, around 6. Baking soda is, around 7. As you get up into household cleaning products that have things like ammonia in it, you're looking at 12 and 13s. Where if you get like your sodas and things, again, Coke has phosphoric acid in it, so it's going to be relatively acidic. We see a lot of acidic beverages, and acids are generally used in a lot of different places. They are obviously used in making fertilizers, various glues and batteries. They're used in plastics and making various rubbers, as well as preservatives. So you see acetic acid. So acetic acid is used as a preservative. You also see things like vitamin C, ascorbic acid. They're generally added as preservatives to things. So acids are used as preservatives in various things. Boric acid is in your eye wash. So for anybody who's at home bored making the slime with your kids, you need the boric acid from the eye wash to help create the plastic, to have the binding agent in the glue to make the slime. Lots of uses for acids. They get used in a lot of beverages. We see them in all kinds of fruit products because ascorbic acid, vitamin C, is acidic. Our stomach acid is hydrochloric acid. We use things like vinegar and stuff like that also in a lot of our cooking. If you watch the cooking channel at any point, inevitably someone will talk about adding something into the solution to give it some acidic you know, to put something acidic in there to break up the compounds or break up the flavors, right? This one I include in here is one of my favorites. It's called Aqua Regia. It's concentrated nitric acid and concentrated hydrochloric acid. And when you mix them together, you get like this bright red solution. So hydrochloric acid is clear, nitric acid is clear, but then you mix them together and you get this bright red acid. And this stuff eats steel and just about anything. So it's a very cool acid. And our bases, obviously bases are used in all kinds of making soaps. It's a fundamental part of making soaps, as well as, you know, electroplating, cement, obviously antacids and cooking. They're also used in fertilizers and obviously other detergents as well. So there's lots of these various kinds of strong bases used in various things. Obviously, we also see like the calcium hydroxide, not just from the not just using cement, but also in the antacids, because they also market it as, you know, giving your calcium as well. A lot of our cleaning products tend to have very strong bases in them. You know, one of the big areas that deals with acids and bases tends to be, you know, pH quackery. You see this in like, you know, anytime you see Gwyneth Paltrow with her alkaline water that she has with lime, you know, which is hilarious. You know, it's like, well, you can't have those two things together. If you are looking for a solution with a higher pH to be alkaline, adding acid to it reverses that process. So if you thought that something being alkaline was good for you, you eliminate that by putting lime in there. But again, they have this like weird thing where they're trying to like say essentially that like fruits and vegetables are alkaline, you know, basically their definition is like that, you know, anything that's vegan is alkaline, which it's like, well, why don't you just call it vegan instead of, but, you know, anyway. So so there's a lot of pseudoscience that revolves around pH as well. But again, our bodies don't care. Your stomach is concentrated hydrochloric acid. It does not care what pH your water is when you drink it, because it gets down here and then it acidifies the crap out of it. And it does not care that it was, alkaline water. It is not alkaline water as soon as it touches your stomach. So you cannot really change your body's pH, at least not from eating various foods, because your stomach doesn't care. You also have things in your body called buffers that we'll talk about in 112 that also keep your body from changing its pH. So there's a lot of pseudoscience that goes into this whole pH region of stuff. But as far as what we have for our stuff here, there are precipitation reactions with acid base, and there are stoichiometry. So a lot of this is duplicative. Again, it's stuff that we will also have. So here we look at an acid base reaction where we have HCl and potassium hydroxide making potassium chloride. Again, the potassium swaps, okay, making potassium chloride. And when you have the hydrogen swapping to the hydroxide, we get water formation, okay? So this would be the molecular equation. You have the formation of liquid water. We separate the ions. Anything that's aqueous gets separated except the water, because it's liquid. We don't separate the liquids. Our spectator ions here are the chloride and the potassium. And so our net ionic equation is the proton plus the hydroxide gives us water. Okay, so same kind of reactions with acid base. And then we have acid-base stoichiometry. Here we have a 430 milliliters of a 0.1 molar HCl reacting with 0.52 molar sodium hydroxide. How much is needed to neutralize the acid? So this still falls under our stoichiometry. We're looking for how much of the base do I need? I'm given the volume of the acid, I'm told the molarity of the acid, and I'm told the molarity of the base. Okay, plus I have a balanced equation. So I basically have a stoichiometry problem. Okay, so we can do acid-base stoichiometry. Now you don't need that though. Here's why. All right. So here is the stoichiometry for this. Okay. Here's the volume, the molarity, the balanced equation, the molarity. So this tells me the volume needed. There is an equation that goes with this instead. So we can take a shortcut, but the shortcut requires this. Number one, that you identify that you have an acid-base reaction. This only works with acids and bases. Okay. This equation does not work if this is a regular stoichiometry problem. Okay, it only works with acids and bases. Okay, so this is very similar to the dilution equation. M1V1 equals M2V2, MAVA equals MBVB. So my molarity of my acid in my problem, okay, my volume of my acid, 430, and my molarity of my base, 0.5, multiply and divide, 88 milliliters. Okay, so you can take a shortcut if we identify that it is acid base. Okay, again, we'll come back to this later. And titrations are something that we would, we're going to do, we'll have another lab. Okay, so again, we're not going to do physically the lab, but I have data for a titration experiment, right? So you will have to do some data analysis for this. Okay. Essentially, this is something we would do and we would have done in the lab. Okay, this is a good, one of the good labs that we have. It's a good skill to be able to do. Essentially, we have a base in our burette, we have acid in our sample, and we add base until we get a color change. We use an indicator, right? And and so we essentially apply basically this kind of equation to where we can kind of find where if we don't know the molarity of that acid, okay, we don't know the molarity of the acid here, but we know how much there is, so we know the volume. We generally know the molarity of the base and the volume, and so we would get the volume from the experiment, and so then you have an MAVA equals MBVB equation, and so that allows you to calculate the molarity of an unknown acid. And so this is what we would have done in the lab, is to calculate the molarity of an unknown acid, which again, and so we can use this to find things like, and so essentially the way a titration works is that at some point, the molarity of the acid equals the molarity of the base. And so through that equivalence, and so this is a kind of graph that we would have, we'll probably talk about this again next time. This would be a graph that, this will be something you guys will deal with more in 112. If you take 112, you'll deal with these kinds of pH curves. This would be something that we would have talked about had we actually done a lab. It's less, it's not used really for test questions for the most part, because we're more interested in calculating these kinds of things. So this is more of like a laboratory thing that goes with the titration curve. So it's less pertinent here, and I'll try and find some other ones. But generally in 112, we do strong acid, strong base. So when you neutralize a strong acid and a strong base, you essentially have this, right? Here's a strong acid and our strong base, which makes water. So almost all of these titrations come out with a pH 7. Okay, so the pH is 7 here these strong acid, strong base reactions. They almost all come out this way because that's where we're making water, right? And so water's pH is at 7, right? And so there's various things, at least in 112, where we can generate other things from this graph that we're not going to do as far as here. So most of what we get from these things is things like in the lab where we do the experiments, and I don't let's say my so we don't have the luxury of doing that, but my but I will have another data set for you to do. You'll probably have to do more of the calculations next time. Say there's this is kind of one of my, I was going to use this in the, I'd use this one in the lab as, this is like the joke of doing the titrations is that, if you're mixing you're mixing a clear acid and a clear base, and if you don't put the indicator in there, you're just making water, right? You're not seeing anything without the indicator. The indicator is an organic molecule that changes upon a pH change, and so you have an acid that's a low pH, and as you're adding the hydroxide, the pH is starting to go up, and then when it hits this neutralization point, you have a stronger pH change, and so it changes color. And so if you forget that indicator, then you're just sitting there titrating, and you're titrating, and your pH is just going up, and so you're just adding straight base, and you don't see anything. And after you've added the whole burette, and then everybody's like, I didn't see anything. It's like, well, then did you put the indicator in there? And people often forget to put the indicator in there. So, unfortunately, I didn't get to, use my meme for the lab. So, all right. So I think we'll probably stop here with this, and then we have one section left. I am going to put together some practice problems. I'll probably do some practice problems tomorrow, and then I will post up a video of those practice problems by Wednesday, hopefully. Again, it's mostly just I'll try and do some example problems.